the final major SAT implementation. I did a little bit of research and I found there's another one, and I can't even remember. It's like someone that had a patent on it, and it's proprietary, and there are some vague descriptions of it. Oh, I wish I remembered the name. Gosh. Uh, what is it? The patent algorithm. Oh, gosh. I think it's called Stallmark's method. So I do have a paper on this one. I don't know if I want to implement this. It was for years there weren't even any research papers, as it was like patented by like some, I don't know, an organization tied to the government or something. So one thing we should, but just when you're doing research and you want to be complete, especially if this is not for, I'm not as interested in probabilistic methods, but this is called Stallmark with a, I guess maybe that's a Dutch name or something. It's got a little, oh, yeah. Okay, Stallmark's method. Again, this is like, and there's a paper about it. I think the patent expired, so now it's okay to use it. But uh, I read something saying it's kind of doing some breadth first search, but of course, I would really, really like to see another method in action as well, to see if there's anything to it. Now, I think the paper there is enough to implement it. Yeah. So there is another method. Of course, none of these are, enough to do the job for polynomial time. So anyways, CDCL, the the trick here is going to be managing a stack that's going to give us enough info. So what we cannot do is we cannot do this strategy where we're, trying the positive and negative um, by putting both the positive and negative on the stack. So, but actually that doesn't happen here. The stack always can. So basically we have to delay putting the negative one on the stack if we're going to try the positive one. And that's all there is to it, because then we can go back up the stack, and we know that the stack is always like a chain. It doesn't have like, other delayed operations. It has only the chain to get to the current point, and that's exactly what we want. So my first, well, there's some problems too, because when we get a conflict, our unit propagation isn't looking for those conflicts. So if there's X and not X, it takes the first one it finds of X and not X, and basically just gets a false clause for the other. But a false clause isn't so helpful because it doesn't. But there is probably some tricks we can use. We're going to have to use some kind of tricks to figure that out. We can change unit prop, but it might break all the other codes. So that's, of course, that might be the best idea, is just to fix things. But for now, I want to see if we can just simply get the whole job done. Now, there's also this idea that with conflict-driven clause learning, you can decide how far back you want to look for conflicts as well. Because you could get more than one conflict. There's a lot of things that could happen here. So my idea, well, first off, if it's SAT, we can probably just do this same strategy. As far as I can see, there's not going to be much difference between the DPLL recursive routine. Again, I don't like recursion. I would like to get rid of it in general, but it sometimes could make it slower in Python. You never know, so it's not like there's an easy answer to some of those things. So solved vars here. Now solved vars we shouldn't have. We have solved. But now this is where things get interesting, because I think we can use the functions we already have. We just need to be really smart about this here. And yeah, we don't need to learn any clauses if we have sat. In fact, there's nothing to be done here. This shouldn't be a pass. This should be a continue. Again, nothing to be done. If it's unsat, then we don't yield a solution. If it's sat, we're going to yield as many solutions as we have free literals. Could be a lot of them, but okay. And if it's, otherwise it's going to do the same exact thing. I mean, there's not really much to say about this part. However, we can only do positive or negative. So what's going to happen is when we take something off the stack, we may need to decide, well, hey, do we need to do the negative variant? One thing we could do is store X on the stack and just say, well, if it's positive, let's do the negative before going back up the stack. So that's kind of like a simple idea for that. So we're going to append to the stack pods CPM a tuple with these things in it. So this starts looking better, but what's going to be the issue here is we need a history of solved variables. So really, we could do it two ways. You could make a list of lists, kind of a nasty thing to do here. Here, we don't need to make a copy no matter what. But since we have the stack, we could also just go through the stack structure. Since it's a list. If it was a real stack structure, it'd probably be annoying to try to have to enumerate through it. So it might make more sense to use like some kind of a vector or this type of data structure. Even in C++, you might not want to use this stack when you actually do want to enumerate through stuff. That's one helpful idea. So I guess we can make this solved vars. The key is if we want, well, actually let's just call it S for now, because we can build solved vars by just concatenating everything together. So solved vars is going to just equal, you know, what is it? Is there like a list join? I think in Python, if we want to join more than two lists, I know plus string join. No, yeah. How do we? I mean, obviously we can do loops. I'm looking, of course, for a clever way to do this. A one-liner. There is definitely, we could use itertools chain. We don't need to worry about duplicates. I mean, we could use set, of course, offers this kind of functionality. All right, do we have itertools? Oh, we're not using itertools yet. Okay. I guess what you do is you set solved vars equal to S, and then you just, you know, for item in stack, solved vars extend you can go through the whole stack and just add on the entries, because what we're going to do is we're going to now say at each phase what unit clauses were solved. Now this would be a problem if we don't actually start finding the initial ones. So we just, you know, say unit prop clauses map. That's the easy fix. So actually there might be some solved right at the start. And of course we want to figure those out and get rid of them. Yeah, I've said there's some optimizations, like we shouldn't choose a free literal. if we're solving based on that, that is just a terrible idea. So yeah, I never fixed that. It's just a little optimization though. I mean, it doesn't hurt anything to do it. It just would make it potentially a lot slower. Because again, we actually, if we have real free variables, we want to end up with them here where we're just going to use all the 2 to the n combinations of solutions that come from those. Those are so straightforward because there's no restrictions on them. So, okay. This, it's okay. This, it's okay. But almost okay. It's not quite okay. So before we continue, we need to think like, well, what about the minus x case? At some point that has to come. Yeah, that's going to be annoying because we do want to continue, but we still need to deal with the minus x case at some point. Oh, but we don't, yeah, actually, no, we need to deal with minus x here and here only. We don't need to do it here. Here can always do positive, and then it's going to keep doing positives until, of course, it hits a sat or unsat, and then it'll have to do a negative branch, which is fine. So we'll have to re-push these things onto the stack. In fact, we don't want to modify them. It's another tricky issue. We make the copy here. Actually, I guess we can because we've already made a copy. So these are meant to be modified. Yeah. So what we would push onto the stack is actually, well, we'd actually have to look at even not these elements, but we'd have to go back and because these are already going to be tainted or corrupted or what have you. So I would almost say we're going to put x on the stack as well, namely our branching variable. And if it's 0, then of course, oh yeah, that's another case. The initial value of the stack, we aren't branching on anything. Actually, we could. Actually, there's no reason why we couldn't. Yeah, it just makes the code look a little uglier. I'm trying to make the code like reasonably simple and elegant, if it's possible. So, okay, so we have our new solved variables. In S. But we're putting the solved variables for this round with the temporary, or that not temporary, but the copied, scratch clauses and stuff for the next one. That is a bit of an interesting choice. The other thing is when we learn a clause, we'll need to go through the whole stack and add that clause. I'll tell you, that's it's adding complications is what it's doing. Anyways, this seems to be reasonable here. Actually, we don't need to do anything in this case. Oh, actually, I don't want to say that, but it's this case where we're going to learn a clause only. But here we still may need to go through the negative one, even if we aren't dealing with the clause learning. So, because we may want to unify this somehow to avoid like excessive code. Okay. All right. I think we're getting ready for the next phase here. So we have the resolved from the previous and the scratch buffer. And actually, yeah, it's not that bad. It's pretty much consistent here. Okay, so this actually is fine. There's nothing to be done there. One idea as well is we can just get this working without clause learning and without backtracking. And that's already like a big step forward. So we would just, do this kind of thing. However, this is where things get like a little bit awkward because well, first off, we don't know if it should be, x or minus x or all that, but what we can do is we can do the same idea. We can put a 0 here. So where you put like a special, we can put a special value. So we want to preserve the solved variables to that point. And actually, we want the same things here, but we want them now with the previous stack clauses. So we will need to recompute the free literals. Yeah, I mean, actually, I'm really happy if we could just get it working like this without even doing the clause learning. Obviously, in here we'll need to do some kind of clause learning and backtracking as well. So there's two issues: clause learning and backtracking. But having this working without clause learning and backtracking at least proves the stack concept and this idea of kind of refactoring. Basically, I'm doing DPLL refactored right now. That's how you start this, and then you can just figure out how we're gonna deal. That's the hardest part for, of course, CDCL is figuring out how to deal with that, especially since there can be multiple options for where you want to cut the implication graph. So the clause learning here is something to delay though until after you have DPLL refactored working. And it's a question if we need to branch on the negative case here. I feel like if we made this so the free variables weren't branched on to begin with, then you wouldn't. But because we've assigned kind of arbitrarily some value, I think we're going to need to, of course, copy all this code here. Well, or refactor it in some way. So we use a variable to indicate that we should continue and do that kind of stuff. Otherwise, the unique code is spitting out solutions and eventually clause learning and backtracking, where we can go back, delete a bunch of things from the stack, and make some new clauses using some simple logic with just using these solved variables and certain looking at the clauses. Although it's going to be trickier because, again, the way that we've updated the clauses, the way we're doing things here. In fact, do we have the original clauses? Because we may not want to lose those. Okay, we don't. Oh, actually, I'm going to change my mind on this. So that now we do. Oh, well, I mean, minus deleting the tautologies. That's fine. Okay, so so first off, map and clauses shouldn't be being used anywhere. This should be M. Map, that's the original map. I don't even know if we will need it. Oh. Okay, that is a poorly... Let's not do that. MP. I'm gonna call this MP because for map, for some reason I used. Just making sure I don't have any references to map. Again, map or clauses should not appear anywhere here. And if we were calling it M, we need to fix that as well. I think we've fixed all of them. Okay, so that takes care of this part. Now, now I get some coffee. That's as simple as that. Returning coffee into code, as usual. So the next step here is to do the same with clauses. Make sure we're doing CS here, as we call them. So we simplify things down a little bit. So far, I don't see any real issues with this. Of course, I anticipate it's going to be a little more of a struggle to get this to work, but the idea is that, yeah, we've just adapted our old code now to using a stack. And what else do we need to do? It almost feels like we're good here, beyond this case. So again, this case is actually like a special situation where we actually want to take minus x. So if x is not equal to 0, of course minus 0, so the 0 is a kind of a nice value. And here we put 0 because we're saying we branched on x already, so we change it to minus x and now stop doing that. And just like at the beginning, we didn't branch on anything, so we can put a 0 in here. So when it, you know, if it was already sat or unsat, it wouldn't do anything extra here. So, but as far as I can see, we need it here too. Or I mean, of course we need it there too. It's not even a question. We know we're going to need it in both of these continue cases. So probably we should just not continue. And we should like maybe set up a flag. So. And then if sat on sat, yeah, we can just use true. If sat on sat, if x is not equal to 0, add some stuff to the stack. Otherwise, just continue. Regardless, we're going to continue. We're not going to, of course, traverse any further. I think this works. Honestly, I feel we're done. I feel we've adapted now. And yeah, that makes the algorithm a little more long. This code is kind of duplicated. Again, it's here as well, a little more efficient because it doesn't recompute the free literals, but... Oh, wait. And there's no hope if we didn't use the right variables here. Okay, I think this is ready to test. All right, let's give it a go. Of course, it did not work. Whoa. False. Okay. This shouldn't, honestly, this shouldn't be that hard. I mean, we're just adapting recursive routine to a stack, so. And this is a very simple case here that's failing. Just going to change this because, again, we're actually modifying the list anyways. No real point in having a separate variable here. Some little mistake in here. The map's empty, the clauses are empty, but one somehow never made it anywhere. I'm sure there's just a little issue blocking this from, oh, whoa. That is not a little issue. Or is it? Wait, I don't know. Oh. Yeah, I guess I kind of forgot that in there. Let's see how that works. Still doesn't work. I see. So there should be 4 solutions here, but we're only enumerating one solution. Overuse of X. Man. Okay, this one actually, it's in a lambda, so but again, that's actually not a good thing to do. To overuse variable names, it just makes your code prone for bugs. So let's call it B for like a bit mask or something like that. No. Oh, but I mean, things changed a little. Do we use X anywhere else in here? Is there? This is the same context for X, so I'm okay with that. We put X here, so it will flip to minus X. You could put minus X and just change this to X. It doesn't really matter. we could actually merge all this code. We could merge all this code. I mean, the only thing different here is this line, this, and this. And that's a big hint that, uh, of course, there's something to be done here. And then we don't use if sat unsat, we actually use if x not equal to 0 or something. Well, first we use sat unsat, but just to set x, and then, yeah, and we can merge all this code together. Actually, that's kind of worth doing, but yeah, so I don't know why we end up without a literal at some point here. Oh, I said this before, Oh man, this is bad. This is very bad because this is not supposed to be the one we use here. Now, we don't need to worry about the case where the stack's empty, because if the stack was empty, x would be 0, and so we don't need to worry about it, which means we can go stacks of -1. Underscore CSMP. Oh. Wait a second. We don't want this solved. We want the previous solved too. No. Oh, wait. Yeah, we want solved. Actually, we do want solved, right? Yeah, I do. I have it here. Wait, why? Oh, that's interesting. Oh yeah, but these are different cases. Yeah, these are. Oh, that's good. Oh, that's so tricky. So actually, there is a certain amount of logic here that is tricky for the context. Where definitely, this is looking right to me. Whoa. Oh yeah. Okay, there's more issues here. We can't pop the stack. We can peek. This is just getting trickier. So the only good place to pop the stack is here. So if x is 0, pop the stack. Okay, there is going to be this tricky aspect to this. And obviously, if we're adding something, we need to keep the stack intact, so we're not going to pop it. The only time to pop it is if we get to sat or unsat, and x is 0. There's just nothing left to enumerate. So okay, so we pop. I see two items are on the stack. I see the 0 here and the 1 here. Okay, I see the problem. Okay, let me get my coffee because this. I mean, this code's going to keep executing, and this is a big problem because we've left things on the stack now, and now it. Yeah, it's just gonna pop and put this right back on because the parent was still on the stack and it like never sees the resolution that it wants. Well, my simple idea right now is just to say stack -1. Just knock this x out, right? that's that's the simple idea. Is say that okay, that should become 0 as soon as we peek at the stack. We never want to actually go through that one again. Yeah, I mean, it means it should just be popped right off because we hit a dead end, and the dead end actually needs to keep chaining up. So we've lost that kind of history on the stack. Because we add the negative value, but when we get here, I mean, so you have something and it's 1 and then 0, and then the one. Oh, we don't pop the 1 value off either, do we? Oh. Yeah, I feel like we need like some. Yeah, that's a big problem. I mean, the first instinct is, well, we're always going to want to pop the stack here. Either we're at the end, or even if we're not, we still want to get the 1 or this value off the stack, because this actually had an x not equal to 0, and we're going to put the other case on. Of course, the x value will be insolved because it will be a unit propagation, but we don't want to care too much about that. Oh, still stuck here. And actually, I mean, that's not that surprising to me. As I said, this stack pop is highly suspicious. I mean, it's better, it should be there, but the problem is it needs to propagate further. So sometimes when something is popped off the stack and this peak occurs, but this has occurred already, we do not want to do it again. A question is, how do we know how far to pop up the stack? If we knew that, that would be enough, but I have a feeling we don't really know that. But then again, if the x value is 0 here, Something like that. No, it's still not working. We know we always want to pop one value, and then we want to pop there's other ways to solve this. I don't know if this is a good way or not, because technically you want to kind of pop a chain of zero values off, but the problem seems to me that this one here might cause a problem because zero means we've already tried the positive value, and we're trying the negative value, but here, like, we haven't tried anything, so it's kind of inconsistent. So I'm looking at what's the x values in the stack are. I see 0, 1, negative 3. All right, we're gonna do this differently. We're just gonna pop here, and we're just gonna edit the stack at this point. Probably I should just refactor this, but I think the easiest thing to do here is just, say stack -1 equals 0. Oh, that's maybe a problem. So we know that it's not sat or unsat here, and yeah. Still doesn't work. Again, it just needs a refactoring at the end of this, and I think everything will be okay. Oh no, not even close. What could be going on here? This initial case is a real problem now. We're getting two solutions here. Yeah, none actually. That's kind of clever because then it'll change it here. Actually, that's not too bad. So it branched on 1 and then -3. So if we look here, 1 and -3, have a unique -2 solution. That's good, I mean, but then 1 needs to branch, it needs to go on to +3 as well. Okay, and 1 +3, and it finds 2. Yeah, I don't know. I'm thinking about it here. Okay, it's working. It's working. So that part works. But then it just comes back down the stack and dies out really quickly. So it doesn't try -1. Why doesn't it try -1? Because we zeroed it. Yeah, this needs to be a little more complicated. I see the problem right here. Obviously, we need to try -1. We can't just zero this because although that's like a preventative measure, now we're going to only get half, or, who knows, but it's kind of like a 50% type of filtering, which is why we only get two solutions. So this is actually not a good idea. At the same time, we need to do something so that when it comes back here, it needs to know if it should do the negative value or the positive value. And plus, it would do itself again. Yeah, that's actually, this is really, this should almost be like a next value type thing, I guess. Oh. But then that doesn't help either. It's like just not having it here. She'll go into that infinite loop. Yeah, this is this shouldn't be that tricky. I don't know what I'm making a mess of this here. It should be easy. It's so close to working, and then we can focus on the clause learning. Again, I can't focus on the main task until we have it structured properly here. I'm not even saying this is ideal, but we can use solved vars and the different clauses and maps to do something to deduce those clauses. It's definitely possible. That definitely can happen. It might not be efficient, but this is enough to start on figuring out the learned clauses and backtracking at the same time. I mean, of course, you want to do those in kind of one step, learning clause and deciding if you've backtracked far enough. We'll pop stuff off the stack. But the problem is we need the enumeration to work. And right now we don't have working enumeration. So we never want to process something more than once. So if we get back to the same stack item, that's a problem. We definitely don't want to do that. In other words, we don't necessarily want to do this, do we? Feels like we don't want to do that. Yeah, it's a wasted operation here. Wait a second though, but actually, yeah, the problem is this one. One. Yeah, it puts -3, but it zeroes itself at the same time. Which is fine. Actually, it's when it gets out to the very outer one, the original. It's when it gets out here. Okay, wow. I think what we need to do is this. I know I'm doing some clever stuff using zero or non-zero to kind of try to force the enumeration here. Oof. So if x is not equal to 0, it really doesn't matter if it's sat or unsat. If it's sat or unsat, we do want to pop off the current progress, I suppose. It's more complicated than that. That won't work either. Oh, this is really like one of those. It's not hard, but the code's almost right. But playing around with the stack is not easy. Think logically. Think logically. I'm making one more complicated. Had a bit of a headache before I see. It's yeah, this is annoying here. Again, okay, so let's think about it. When we toggle, well, when we process a value, as I said, we never want to process it again. But we can't put extra values on the stack either up front. That would be the easy solution. It doesn't work either because we need to be able. Oh, I mean, maybe we could get away with it, but it's going to make this backtracking really inefficient to try to play with the stack. We want the stack to basically be already, uh, in order, and even if this is considered non-chronological, it'd just be popping extra items off the stack while we add learned clauses. So if x is not equal to 0, feel like there's three cases here, and this is why I'm having a problem with this, because obviously the first time we go through it, the first time we go through anything, we do the unit prop, and we don't want to ever do it again, and we don't want to check sat or unsat. So up here we want to say, like, if it gets back to a node that it already had processed, we want to kind of move on to the next one. At the same time, one could have pushed itself back on the stack here. It could have done the -1 here. That's what should have happened. But it didn't happen because one, yeah, because it changed here. Okay. I'm almost going to put it back to the way it was right now for the time being. There's only like 3 or 4 cases that we need to solve, but you have to be very precise with this type of code. So yeah, something has to give here. So when it returns back to one that it's already done, it needs to change to its flipped value. I feel like I need another state variable on the stack. No matter what I'm coming up with here, it's always like, I don't like introducing extra things on the stack. That's always like kind of adding a certain complexity if you don't need it. But if you do need it, you do want to put there. The point is, I don't know when we've gotten back from a child, basically. I have no idea. Because actually, right now I'm letting the enumeration occur by its siblings, basically. So because of that, actually, it should be the same exact code here. Yeah. But first, it should do its children. So that's the idea. First, it triggers its children, and then it does itself. So I guess the real question is, do we know if it's done its children or not yet? And is there any way of telling? Well, you can't use something like solved because it's not guaranteed there. Oh, wait a second. It is guaranteed because it has to solve one because we put in that's really tricky. That's using the information we have to our advantage. Oh, that's great. So what we could say is, ooh. I mean, we know this one doesn't work. It's an infinite loop. But what we can say now is we can break the infinite loop because we can, instead of moving on to children again, we can move to siblings. And that's what we have to do. We have to force it to siblings here. In fact, the way we want to do that is by looking at this. Just to make sure that it should give like 50% of the solutions again. Oh no, because it always puts the solved into the next one. Yeah. Okay, so if it's always putting the solved variables into the next one, this is kind of an annoyance here. Because when we get back, we're actually having the previous ones solved variables, not the current ones, which won't help us at all, I don't think. Yeah, it won't help us at all. Yeah, again, the easy thing to do here is to just stop the nonsense. And of course, we don't have apparently anything in our stack. Yeah, that's convenient. And this value isn't enough either to tell us if we've done the children or not. We just have no idea that this happened. We don't know if this was pushed on the stack previously and it returned to it, or if it just got pushed on here. We just don't. This information just isn't available with the way we've done it right here. So to get the information of whether we're on the stack or not, we can either put another field in here, a true or false, enumerated children already, or option number 2, I guess we could modify a tuple in here to indicate that, but I don't like that particular either. But if we've enumerated the children already, so actually it hit here, then we know we just want to yeah, we just want to do the minus x case. Oof. So, I mean, enumerate children will be just false here. I think this is the way to go. Enum children. Have we enumerated this one's children? False. 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 So this is sibling and this is children. I mean, I'm not saying I'm particularly enjoying that, but it works. So if it already enumerated the children and it gets to that point, just continue. Otherwise, we know it's false. Again, we can kind of rewrite this later, but that's... So if it enumerated the children, continue, but we pop always. But now we actually have to put ourselves back on the stack. Okay, as this whole thing. But with the true here. It's maybe not, yeah, maybe we should not use a tuple here and we should use a mutable structure. Anyways, basic idea is there though. In fact, we could even just use a map or something like a visited type of, or yeah, actually this is probably more smart would just be to not even put this in here so we don't have to micromanage it. Just add a visited set. We could just keep track of a set that keeps track of X's that have already been visited, and it could just say if it's in that set. That's actually much nicer. That's easy to fix. What's harder is to make sure that this new logic is going to work here, because we have one more problem, and that's if it enumerated already the children. Actually, yeah, that's a problem too, right? Actually, we want it there. Yeah. Again, we're still stuck at the same place, but now we're a little bit less stuck. Yes. Yes. Okay. Oh man. Okay, I made that too complicated. I almost think the visited is just worth it here. I don't particularly like adding more and more stuff to the stack when we want it to be. Oof, yeah. I mean, the simple thing to do is just put visited here, and then we can just make this query a lot easier, and we don't need to do this anymore. So it's this X that we visited, not the new one. That's fine though. Uh, ooh, this won't. Will it work? Hmm. Okay, we're not doing this. It's a nice idea, but the problem is these zero values in here are gonna just create more and more confusion, because we can have zero and true, and then we won't have a way of doing such a query. In fact, then we probably would just put minus x. Yeah, okay. There's lots of ways of doing this, but I don't mind right now because this works. This was the setup, and now we have a setup so that we can do the clause learning. Can even profile the time here. Oh, you're gonna need this eventually anyways, so let's just see how. Of course, we're gonna have to sit here waiting for DP to work, but you know, it's really nice to see this actually works now. As I said, there was a three-state issue, and this is like the way of thinking about, oh, look at the time. That's amazing. CDCL is significantly faster than anything we wrote, and we haven't even done CDCL. All we've done is adapted to a stacked data structure. That must be a coincidence. It's too weird. That is weird. Yeah, it must have been a coincidence. Now the times are much more similar. Yeah, this is what I expect. The times should be very, very similar. Again, we're seeing times are very similar, and that's exactly fine. Because again, we didn't change the algorithm at all. We just kind of changed the data structures and the way that it, doesn't have to call functions now. It stays in one function, but again, it kind of got a little complicated with the way this works. I particularly don't like this. In fact, we could do this with a one line. I mean, maybe this is a nicer idea. But it's still not wonderful. Just because, you know, we can hack that one line in. Again, we could always change to mutable data types, but the other option is to keep track of the x or minus x values we already visited so that we stop this. And I think there's a clever way of doing that. In fact, will we need x at all? Oh, we'll still need it to make the query. Yeah, we will. But we don't use it much anymore, which is good. We almost don't touch it. But the fact that this works is impressive. And now we can move here and we can start writing clause learning code. The question is, do I want to do it right now? Because it's going to take some time. But this was the whole goal. The whole goal of the task was to get the information we need. Now we actually have a bunch of groups of solved variables per x. Oh, you know, this isn't going to work because we need to know the x. Oh, so this doesn't work anyways. We have to refactor. We have no choice because a 0 isn't going to be telling us anything here. Oh, yeah, that's true because we need to know the value that is here. So actually we want this to be minus x. Oh, and then we need to like... So this is sibling continuation here. Okay, but we don't use x much, as I said, so x here. This is straightforward. This code can even be combined too. That's the neat thing about this. All of this can kind of combine together. The only place I want it to be 0 is here. Oh, I'm of course risking screwing everything up here. Ah, the risks. Right after I take out all the debugging code, back to the drawing board here. Yeah, this is finicky type of code, but again, I want the information because of course I know I need that value right up front. There's no doubt about that. I don't like the old. I like this new idea. It's much better. It's much cleaner. Oh wait, not x indices. That's not gonna work. I guess it doesn't guarantee we visited its children, but it either visited its children, or oh wait, this doesn't work either, huh? It doesn't work because we could end up in different branches of the tree. We may have to visit. Yeah, this doesn't. This is not. You can't globally do this. Okay, I'm backing out. Oh, all of the change. We're getting it back to working again. Realizing this. Maybe we're stuck with this. All right. I mean, the only thing I want to change here is this. I just want minus x in here. I could always add another field, but I don't want to do that. Um, all right. Well, I need to be careful with this case. I'm not sure how important knowing the branching variable is, but obviously I would like to have minus x in there. Problem with that is I'm using it here in a kind of tricky way. And if I put minus x, there's no way we can detect anything about it here. I don't think. Then again, yeah, we won't be able to detect. Because now we need to know if it branched on its siblings, not just its children. We have the enumerated children, but enumerating its sibling was like, well, there's only one sibling, so we can just zero it. But now, if I actually don't want to zero it, that's a different issue. And yeah, again, we can't use a global structure for this either, because we could have the values coming back. Okay, for now, I'm not going to worry about that as much as I'm going to worry about like trying to learn a clause and trying to backtrack here. Maybe we don't need to know more than the fact that it's any. We know that the learned one is going to be in solved vars. We know it's somewhere. It's going to have unit propagated because we added a unit clause. So we technically have it. It starts to raise the question if we even need this x at all, or if we could just use booleans. Well, actually, we do because because we have to add the clauses. I mean, we could, but there's different. We could even put the clause next clause or some other. There's lots of ideas for this. Anyways, I kind of like the way that it works right now. If this is going to turn out to be sufficient. So the problem with this unsat case is we don't know which one of these variables led to it. That is a big problem. And so, um, we know that one of the variables, one of the new unit clauses had to be the conflict. One or more. So the question is, first off, which variables caused a conflict? Which ones caused empty clauses? The truth is, we absolutely have no idea right now. We could determine it, though, by taking this solution like this. We could, combine it together and then apply it to clauses. And again, we won't be able to use unit prop then. We'll actually have to use something like that detects which variables are causing empty clauses. And that should be possible. Again, it would be nice if unit prop would actually tell us that information. Probably that's how we should do it. Even if we don't need the information for the other algorithms, unit prop could easily check these 0 unsat cases. Yeah, and if it simply gave the variable that caused it, that would be the problem is 2 variables with unit props could have caused it, and so I'm thinking that it's a big problem. You do have to think about that. You can't just make any assumptions here. So yes, I do see that case, and I do understand it's important to figure that out. So no doubt here. Yeah, I have to think of a solution to that. So I would say then that we could either write another function which figures out like because we'll have all the unit props done, so we'll have all these kind of quote unquote solved variables. But again, we don't know, some of them it could have solved the negative x instead of x, and it would have, so the question is, when you solve all of those, which ones of those variables are in clauses that became empty, which could actually, become empty to the point that we've lost the clause information. So we're going to kind of like want to track things a little more here. In fact, we don't need to do this at all. We could just focus, we could just focus on this removing minus x from clauses. And the question is, actually, I think that's the easiest way to do it. We just go through every clause and we see if all of the variables in the clause are covered, and we're done. And then we know the variables too. Yeah, that's actually that's nice, because that's at least relatively. Again, actually, we shouldn't have to be going through things extra times here, and this kind of is, but it's not bad. So the first thing we need to do is we need to do this. Again, we're not going to use solve vars, so we're free to extend it here. Now, yes, one or more of the new ones had to be the conflict, but we know that it could be conflicting with old ones potentially too. In other words, x was forced now, but minus x was forced a long time ago. So minus x might be the one in the solved variables. Yeah, anyways, that could happen. So the key now is that we should be able to find a conflict by just saying for a clause in clauses. And then we could actually just subtract. Actually, it doesn't really help to convert this to a set, because subtraction with a list is just as efficient. It's just going to enumerate. So we can just say clause